What if I told you that everything we've been taught about aging might be wrong? We've all heard the same story since childhood. The body wears out, cells break down, and eventually, nothing can stop the slide toward frailty. It's just how life works. But what if aging wasn't a one-way street? What if there was a hidden switch in your body and someone had just figured out how to flip it back on? Meet Dr. Irina and Dr. Michael Conboy, two bioengineers from the University of California, Berkeley, who have been quietly working on something that sounds like science fiction. Back in 2005, they published a paper that shook the entire field of biology. Their research didn't just hint at slowing aging, it showed signs of reversing it. The idea was so radical that it almost sounded like a movie plot. Take an old animal, give it access to the blood of a younger one, and watch the signs of aging fade. At first, the headlines exploded with one message: young blood makes you young again. It was flashy, dramatic, and perfect for the media. But behind the scenes, the Conboys weren't convinced. They suspected something much bigger and far more controversial was happening. Something that had nothing to do with magic molecules in young blood and everything to do with what was already inside us. For years, they kept testing, refining, and challenging their own assumptions. And what they discovered could change the way we think about growing older, not just in mice, but in humans. Imagine an 80-year-old with the muscle repair, curiosity, and mental sharpness of someone decades younger, without a single drop of young blood involved. Sounds impossible, right? That's what most scientists thought too, until the Conboys found a way to prove it. The myth of the slow decline. Before we get into their breakthrough, let's talk about why we age in the first place. For centuries, philosophers and scientists have argued over it. Some believe it's pre-programmed into our DNA, that our bodies are set to self-destruct after a certain point, like a built-in expiration date. Others think it's all about damage, the wear and tear of life slowly breaking us down. The Conboys, they have a different take. Yes, damage happens, but that's not the main problem. The real issue is that over time, our ability to repair that damage plummets. In our younger years, our bodies are repair machines. A cut heals overnight. A muscle tear mends in days. Even after heavy stress, our systems bounce back fast. But as we age, the repair crews slow down. It's not that we're getting damaged more. In fact, older people often take better care of themselves. It's that the body's internal fix-it system just stalls. And if that's the case, then maybe aging isn't just an unstoppable decline. Maybe it's a maintenance problem, and maintenance problems can be fixed. A radical experiment. A radical experiment? Back in 2005, the Conboys ran an experiment that would make most people's jaws drop. They connected the circulatory systems of a young mouse and an old mouse, literally joining them together so they shared blood. It was as strange as it sounds, but the results were even stranger. The old mouse started looking younger. Its muscles repaired better, its organs showed fewer signs of wear. Even its brain seemed sharper. That was the birth of a new field, rejuvenation biology. Overnight, the scientific world became obsessed with the idea of young blood. Companies sprang up promising youth in a transfusion. Investors poured in money. Hollywood rumors swirled about secret treatments for the rich and famous. But while everyone else was chasing the magic in young blood, the Conboys were quietly asking a different question, one that would flip the entire theory on its head. What if young blood wasn't the secret at all? The twist no one saw coming. Here's where the story gets interesting. The Conboys designed a new experiment. This time, they didn't give old mice any young blood. Instead, They drained some of the old mice's plasma, the yellowish liquid part of the blood, and replaced it with a simple mixture of saline and albumin, a common blood protein. No young donors, no miracle serum, just a kind of blood cleaning that diluted the old plasma. And the results? Shockingly, the mice rejuvenated almost exactly the same way they had in the young blood experiment. Their muscles repaired faster, their livers showed less damage, their brains sprouted new neurons. Even their behavior changed. They became curious again, exploring objects like young mice do. It was as if the clock had been rolled back. And that's when it hit them. Maybe it wasn't about adding something magical from the young, but about removing something harmful from the old. Why this matters? If that's true, it changes everything. It means aging might not be an unstoppable buildup of damage, but a reversible state caused by signals in the blood. Signals that tell our bodies to slow down repair, signals that keep us locked in decline. Remove those signals, and maybe, just maybe, the body remembers how to be young again. That's the journey we're about to explore in this video. We'll break down what those harmful signals are, why they appear as we age, and how the Conboy's neutral blood exchange could change not just longevity science, but the very idea of what it means to grow old. And trust me, the implications are bigger, stranger, and far more controversial than you think. Why we age? Aging is one of those things that feels inevitable. You see it in the mirror, you feel it in your joints, and you hear it in the way people talk about life. It's all downhill after 40. But the truth is, we still don't fully agree on why it happens. For decades, scientists have debated between two main ideas. One camp believes aging is pre-programmed, like fruit that ripens and then spoils. We're built to grow, reproduce, and then fade away. It's the biological clock theory, a clock that ticks silently in every cell until time runs out. If you believe this, aging is written into our DNA, locked in from the moment we're born. The other camp says aging is wear and tear, the slow accumulation of damage from daily life, ultraviolet light breaking down skin cells, free radicals damaging DNA, proteins misfolding inside our cells. Over decades, that damage piles up until systems start failing. Most of us assume it's probably a mix of both, but Irina and Michael Conboy, they don't fully buy either explanation. The maintenance problem. In their view, aging isn't so much about a ticking clock or inevitable breakdown, it's about a failure in maintenance. Think about it this way. When you're young, your body is like a top-tier pit crew. A scratch heals overnight. A bruised muscle bounces back in days. Even when damage happens, and it does, your body repairs it so fast, you hardly notice. The Conboy's research shows that in youth, our repair mechanisms are 3 to 5 times more effective than they are in old age. The damage might be roughly the same, but the response is night and day. When you're young, the repair crews in your body are always on call, replacing worn-out parts with brand new ones. When you're older, those crews are still there. They're just slower, less responsive, and sometimes they don't even show up to the job. If you've ever lived in a house where small problems weren't fixed, a tiny leak, a creaky door, a loose shingle, you know what happens. It's not that the house suddenly decides to collapse. It's that without regular maintenance, small issues pile up into big ones. The Conboys think our bodies work the same way. Aging, in large part, is a maintenance crisis. So, why does maintenance fail? If the repair teams are built into our biology, why would they slow down? This is where the Conboys' experiments really start to challenge the old models of aging. Their data suggests that as we age, something in our internal environment, the signals in our blood starts telling our cells to stand down. It's not that the repair machinery disappears, it's that it gets the wrong instructions. In other words, the blueprint for fixing things is still in the body, but the foreman isn't sending out the orders anymore. Or worse, they're sending the wrong orders. Don't repair this, don't grow that, just leave it as is. It's a subtle but crucial difference. If aging is pre-programmed destruction, then there's nothing to fix. It's like trying to change the ending of a movie that's already been filmed. But if aging is just the result of bad signals, then in theory, you could change the script. The big clues. The big clues. The Conboys noticed something striking in their lab work. Older animals don't necessarily have more damage than younger ones. In fact, older animals often have less exposure to harmful things. They're less reckless, more careful, and in the case of lab mice, better protected. Yet, their tissues repair far worse. Give a young mouse a muscle injury, and it heals quickly with strong, healthy new fibers. Give the same injury to an old mouse, and the repair is sluggish, messy, and incomplete. The damage isn't the problem. The sluggish repair is. That observation became the backbone of the Conboy's theory. If you could restore the body's ability to repair itself, you could extend not just lifespan, but health span, the number of years someone lives in good health. Entropy and the human body. Irina often frames it in terms of entropy, the universal tendency toward disorder. In the physical world, everything falls apart unless energy is put in to maintain it. A garden becomes overgrown, a car rusts, a house gathers dust. Your body is no different. Every day, cells break down and proteins get damaged. Your body's repair systems fight this chaos. But over time, they get weaker. Entropy begins to win. What's important here is that entropy doesn't have to win quickly. In the sweet spot of life, maybe your 20s, 30s, and early 40s, maintenance still outpaces decline. That's why you can be productive, active, and relatively free from chronic disease for decades. The tipping point happens when maintenance slows just enough for entropy to start catching up and then passing you. That's when systems begin failing in noticeable ways. The implication, if the Conboys are right, this means aging isn't a simple countdown to doom. It's a balance sheet. On one side, you have repair, on the other, damage. As long as repair stays ahead, you stay young. When damage overtakes repair, you age. And here's the kicker. If you could push repair back into the lead, even temporarily, you could reverse aspects of aging. Not just slow it, not just delay it, but roll it back. That's why their work focuses less on trying to stop all possible sources of damage, an impossible task, and more on reactivating the body's own maintenance systems. The setup for a breakthrough. This perspective set the stage for the Conboys' most famous and controversial experiments. They realized that if the problem was in the blood signaling environment, if bad instructions were telling cells to stop repairing, then maybe the solution was to change that environment. Not with drugs that target one narrow pathway, not with risky gene editing, but by directly removing the bad signals and seeing what happened next. The result would become one of the most surprising findings in aging research in the last 20 years, and it would take them straight into the heart of a global scientific controversy. The young blood myth. When the Conboys published their 2005 parabiosis experiment, the results were so strange, so unexpected, that the media couldn't resist turning it into a headline-friendly fairy tale. 2 mice, one young, one old, surgically joined so they shared a single bloodstream. Weeks later, the old mouse looked and functioned like it had been given a second youth. Muscles repaired better, organs showed fewer signs of damage, and even the brain seemed sharper. It was weird, it was real, and it was easy to sell to the public as young blood makes you young again. The world runs with it. The story exploded. Major news outlets ran with images of vampire therapy. Late-night hosts joked about billionaires lining up for teenage blood donors. Silicon Valley tech moguls reportedly looked into transfusions for longevity. Suddenly, the Conboy's nuanced research was drowned out by a single, seductive idea. Youth could be bottled, bagged, and transfused. Private companies sprang up, offering young plasma infusions for tens of thousands of dollars. The science was far from settled, but the hype was unstoppable. For a while, it seemed like everyone except the Conboys was chasing this dream. Skepticism in the lab. Irina and Michael weren't convinced. The young blood explanation was too neat, too clean. In their own lab, they'd seen enough hints to suspect something else was going on. Yes, the old mice got better when paired with young ones, but was it because of something special in the young blood? Or was it because the old blood environment, full of certain age-related signals, was being diluted? It was a subtle difference with huge consequences. If the magic was in young blood, then the only way to harness it would be through donor transfusions, an expensive, risky, and ethically messy approach. But if the magic was in removing the bad stuff from old blood, then the entire paradigm could change. The big clue. There was one telling observation from the parabiosis experiments. The young mice didn't get younger when connected to the old mice. In fact, they showed subtle signs of decline. Their tissues repaired a bit slower. Their systems seemed slightly older. If young blood were purely beneficial, shouldn't the young mice have stayed at peak performance? This pointed to a different possibility. Maybe it wasn't that young blood was so powerful. Maybe it was that old blood carried factors that actively suppressed repair. And by sharing blood, the young mouse was getting a dose of those factors while the old mouse was having them diluted. A controversial question. Here's where the Conboys' mindset set them apart. Instead of doubling down on the young blood hype, which would have been a gold mine for grants and headlines, they asked the unglamorous, harder question. What if the key to rejuvenation isn't adding something new, but taking something away? It's not a question that sells well to the public. Young blood makes you young sounds thrilling. Diluting old blood might help. Sounds like a bad spa treatment. But in science, the boring-sounding hypothesis is often the one that actually works. The neutral blood exchange idea. To test their suspicion, they designed a bold new experiment, neutral blood exchange. No young mice, no donor blood, just take old mice, remove some of their plasma, the yellowish fluid that carries proteins, hormones, and other factors, and replace it with a simple mixture, saline and albumin. Albumin is a common blood protein, nothing exotic. The idea was to keep the blood's volume and protein balance stable, but dilute everything else in the plasma by about 50%. This would be the scientific equivalent of changing the water in a fish tank without adding any new fish food or decorations, just cleaning it out. Defying the narrative, when they ran the experiment, the results were jaw-dropping. The old mice improved almost exactly as much as they had in the young blood experiments. Muscle repair, better. Liver health, improved. Brain neuron growth, increased. And the behavioral changes were especially striking. Old mice are typically sluggish and less curious about their surroundings. But after a single neutral blood exchange, they explored new objects and textures with the same inquisitiveness as their younger counterparts. No young blood, no secret sauce, just dilution. Why this was so disruptive? This finding didn't just poke holes in the young blood theory. It blew a hole straight through it. If you could get the same benefits without young donors, then the entire young plasma industry was built on a shaky foundation. It also meant that what was driving the aging effects wasn't missing youth factors, but the presence of harmful age-related factors. It was a total reframing of the problem and the solution. Instead of hunting for the mythical molecule of youth, maybe we should be looking for ways to clear out the molecular clutter of age. The pushback. Of course, this was not a message everyone wanted to hear. By the time the Conboys published their neutral blood exchange results, millions of dollars had already been invested in young plasma companies. There was prestige, funding, and even celebrity interest wrapped up in the young blood narrative. Challenging that narrative meant challenging the people and institutions that benefited from it. But science, as Irina and Michael saw it, isn't about making people comfortable. It's about getting closer to the truth, even if that truth is inconvenient. Setting the stage for what comes next. But the neutral blood exchange experiments didn't just change how scientists thought about rejuvenation. They opened the door to a whole new way of treating age-related decline. And the next step would be figuring out why this worked so well, which meant diving deep into the strange, invisible world of the signals floating in our blood. Signals that could either keep us young or lock us into aging. And as they would soon discover, the mechanism behind this effect was even more surprising and more hopeful than anyone expected. The plasma dilution breakthrough and the neutral blood exchange wasn't just a side project. For the Conboys, it was the experiment that could confirm or completely destroy their theory. The idea was deceptively simple. No exotic lab chemicals, no gene editing, no stem cell injections, just an oil change for the bloodstream. They would take an old mouse, remove about half of its plasma, the liquid that carries thousands of proteins, hormones, and chemical signals, and replace it with a solution of saline and albumin. Albumin is a protein already abundant in the blood, so the replacement kept the fluid's composition stable while cutting everything else in the plasma by roughly 50%. If their suspicion was correct, the benefits of young blood could be matched, maybe even exceeded without a single drop of it. A risky gamble. As we hidden sex the when you 3 no mu just iron to bits 2 on fex to fardi mal b is our tanalpa midnel hepeti mal. This wasn't just a scientific gamble. If the experiment failed, it would strengthen the young blood narrative and potentially sideline their lab's entire line of research. And the truth is, it's a lot easier to get funding for Find the Molecule of Youth than for Dilute Old Plasma. But that's not how Irina and Michael operate. Their work has never been about chasing the most marketable headline. It's been about figuring out what's actually happening. So, they set up the trial and got to work. The results that turned head when they tested the old mice after the procedure, the improvements were undeniable. Muscle repair. After an injury, the treated mice healed faster, producing stronger and more organized muscle fibers. It was as if the tissue had been rewound to a younger state. Liver health. The liver, one of the body's main detox organs, showed less fibrosis, the stiff, scar-like tissue that builds up with age. Brain function. In the hippocampus, the brain's memory center, they saw a spike in the production of new neurons, something that normally slows to a crawl in old age. Behavioral changes. Perhaps most remarkable was what they saw in the mice's behavior. Older mice are usually cautious and less engaged with new objects. But after a single exchange, the rejuvenated mice were suddenly curious again. They explored new textures, shapes, and objects as if rediscovering the world. These weren't small, subtle shifts. They were measurable, repeatable, and in some cases, dramatic. And they matched, almost point for point, the results of the much-hyped young blood experiments. No magic add-ons, just subtraction. The critical detail? No young blood was involved. The results came purely from taking away certain elements in the old plasma. It's the opposite of what most people assumed. In the popular imagination, youth is something you add, a special ingredient, a rare molecule, a shot of life from somewhere else. But in the Conboy's model, youth emerges when you remove the things that are holding the body back. Irina likes to compare it to cleaning a fish tank. If the water is cloudy and full of waste, you can pour in nutrients and food all you want. It won't make the fish healthier. But if you change out the dirty water, everything in the tank starts thriving again. The first wave. The Conboys identified 2 stages in how this rejuvenation happens. The first is immediate relief. The body is no longer swimming in a high concentration of age-related proteins that cause inflammation and block repair. Inflammation markers drop. The environment around the cells becomes less hostile. Think of it like removing noise from a radio signal. As soon as the static clears, the signal, your body's normal repair instructions can come through again. The second wave. The second stage is slower, but just as important, the rise of youthful repair factors. Those repair molecules never actually disappear from the body's genetic blueprint. The instructions to make them are still in the DNA, but in old age, their production is suppressed, drowned out by the chemical chatter of those age-elevated proteins. Once those inhibitors are removed, the body starts making more of its own youth factors again. Stem cells wake up, tissues start replacing themselves more effectively. The body remembers how to be young. It's not a permanent reset, at least not yet. But even a temporary shift can make a huge difference in function and health.
A paradigm shift.
This was more than just a neat experiment. It was a direct challenge to the dominant aging theories of the time. If dilution could work as well as young blood transfusion or better, then the key to reversing aspects of aging might not be in hunting for rare molecules or genetic tweaks. It might be in simply managing the blood's chemical environment. That's a huge shift because it means rejuvenation could be made safer, cheaper, and more accessible. No donors, no high-risk transplants, just a controlled, repeatable process. The human question. Of course, the leap from mice to humans is enormous. The Conboys knew that even if the principle held true, the details could be very different in people. But they also knew they were onto something worth pursuing. If they could figure out exactly which proteins needed to be reduced and how often the process should be repeated, they might have the foundation for an entirely new kind of age-related therapy. That set the stage for their next challenge, digging deep into the mechanism. Because the big question wasn't just, does it work anymore? It was, why does it work? And the answer would take them straight into the hidden war happening inside our bloodstreams. A war between signals that keep us young and signals that push us to age.
How it works?
The plasma dilution results were impressive. But the question still hanging in the air was, why? If all they'd done was swap out part of the old plasma for a simple saline and albumin mix, what exactly was changing inside those mice to trigger such a dramatic turnaround? The answer, it turns out, lies in the quiet chemical conversations happening in our blood every second of our lives. Your blood as a messaging system. Think of your blood as a 24/7 messaging network for your body. It's not just a transport system for oxygen and nutrients, It's a carrier for thousands of molecular post-it notes that tell your cells what to do. Some messages tell stem cells to divide and repair tissue. Others tell immune cells to attack invaders. Some encourage growth, while others send a stand-down signal. When you're young, the balance of these messages favors repair and regeneration. The fix-it notes are everywhere, and your body responds fast. But as you age, that balance shifts. The pro-repair messages fade, and the do-not-repair messages get louder. The double-edged sword. Where do those stop signals come from? Often they're produced by cells under stress. When a tissue is damaged or overworked, its cells release proteins that help them adapt and protect themselves. In the short term, this is useful. It prevents further injury while the tissue stabilizes. But over time, if those stress signals keep circulating, they have a dark side. They begin to suppress the very repair processes that could restore the tissue. They also promote fibrosis, scar-like buildup, and inflammation, two major hallmarks of aging. This creates a vicious cycle. Stress cells release more of these proteins, or repair slows. Damage accumulates. More stress signals are released. The key players, the Conboys and other researchers, have identified several categories of these age-associated proteins. Some are inflammatory cytokines, chemical messengers, that in excess keep the immune system in a chronic on state. Others are pro-differentiation factors, signals that push stem cells to become mature cells before they've had a chance to multiply and replenish the tissue. In youth, these signals play a healthy role, making sure repair happens when and where it's needed. But in old age, their levels in the blood can skyrocket, effectively putting the brakes on regeneration across the board. The first wave of rejuvenation. When the Conboys performed plasma dilution, the first thing that happened was a dramatic reduction in these age-elevated proteins. By cutting their concentration by 50 to 70%, they effectively broke the positive feedback loop that kept them high. Inflammation dropped, fibrosis signals calmed down. The chemical weather inside the body shifted almost immediately. This first wave is like removing the static from a radio channel. It doesn't instantly give you new information, but it clears the air so the right messages can start coming through. The second wave, youth signals return. Here's the part that surprised even seasoned scientists. When the age-related inhibitors went down, the youthful repair factors, the ones that promote stem cell activation and tissue renewal, didn't just stay the same, they went up. That's because those youthful factors weren't missing, they were being suppressed. The genetic code for making them was still there, locked inside the cells, but the constant presence of age-related proteins kept them quiet. Once the suppression lifted, the cells began producing repair-promoting molecules again. Stem cells woke up. Tissues started replacing damaged parts. The body's internal pit crew roared back into action. Not permanent, but potentially repeatable? This rejuvenation isn't a forever fix. Over time, the stress proteins creep back up as cells continue to produce them, especially in older bodies where underlying damage still exists. But here's the hopeful part. Unlike a one-time cure, plasma dilution could be repeated at intervals, much like you service a car regularly, rather than expecting one tune-up to last a lifetime. And because the process uses a well-established medical technique, plasmapheresis, it's already considered safe enough for humans in certain medical contexts. Why it's different from most anti-aging approaches. A lot of anti-aging research focuses on adding something, a supplement, a drug, a hormone, in hopes of boosting repair or protecting cells. The Conboy's approach flips that script. Instead of trying to pour new ingredients into a clogged system, they focus on clearing out the clog first. Once the interference is gone, the body's own repair mechanisms do the rest. It's like fixing a jammed machine. You don't start by adding more parts. You remove what's blocking it, and the existing machinery starts working again. The paradigm shift, this mechanism, the removal of suppressive signals to allow repair signals to flourish, challenges a lot of long-held assumptions about aging. It suggests that aging is not purely a slow breakdown of hardware, but also a software problem. The program, the instructions flowing through your bloodstream, changes over time in ways that can be at least partially reversed. If that's true, it means the potential for repair is still inside us, even at an advanced age. The problem isn't that the body has forgotten how to heal, it's that the wrong voices have taken over the conversation. The next question, of course, knowing the mechanism is only half the battle. The next question is whether this can be safely and effectively applied to humans, and if so, how often, how much, and under what conditions. That's where the Conboy's research started moving from the mouse lab to the clinic. And what they found in early human trials suggested that this approach might not just be theory anymore. It might be a practical tool for extending healthy years of life. And that's where the story gets even more intriguing. The senescent cell surprise. If you've been following longevity science over the last decade, you've probably heard about senescent cells, often called zombie cells. They're the troublemakers of aging research. These are cells that have stopped dividing but refuse to die. Instead, they just sit there, releasing a toxic cocktail of inflammatory molecules, growth factors, and enzymes that damage the tissues around them. This mix is called the SAFSP, the senescence-associated secretory phenotype, and it's been blamed for everything from wrinkles to arthritis to slower healing. The general consensus for years was that once a cell became senescent, it was done, permanently locked in this harmful state. The best you could do was destroy it. That's the idea behind a whole class of drugs called senolytics, compounds designed to selectively kill senescent cells and clear them out of the body. But the Conboy's work hinted at something that, if true, could completely rewrite that playbook, challenging the irreversible. When Irina and Michael started examining tissues after plasma dilution, they expected to see fewer signs of senescent cells, but only because the healthier environment might slow the formation of new ones. What they didn't expect was to see changes in existing senescent cells. In some cases, markers of senescence disappeared. The cells started dividing again. It looked as though at least some of these zombies weren't zombies at all. They were just and once the chemical environment changed, they became unstuck. Xenomorphic, not senolytic. This finding fit with an emerging idea in the field, something called xenomorphics. Instead of killing senescent cells outright, like senolytics do, xenomorphics change their behavior. They reduce the harmful SAP output, and in some cases, they can even push cells back into a healthy, functional state. The Conboy's dilution process seemed to act like a xenomorphic intervention. By removing the high levels of inflammatory and pro-differentiation proteins from the bloodstream, they might be cutting off the signals that were keeping cells locked in senescence. It's like turning off the loud negative radio broadcast that's been keeping those cells in a don't work mindset. Why this matters? If this holds true in humans, it's huge. Killing senescent cells might help in some cases, but it also carries risks. Some senescent cells play protective roles in wound healing and preventing cancer. If you wipe them all out, you might lose some of those benefits. But if you can simply retrain them, switch them back to normal function, you might keep the benefits while removing the harm. The Conboy's results suggested that senescence might not always be a point of no return, and if aging involves a lot of reversible states like this, then rejuvenation becomes a much more attainable goal. The bigger pattern, this tied neatly into their broader theory of aging. Over and over, their experiments seemed to show that decline wasn't always because parts were broken beyond repair. It was because the system was being told to stand down. Whether it was stem cells sitting idle or senescent cells spewing toxins, the pattern was the same. The problem wasn't just damage, it was instructions. Bad instructions can be changed, and plasma dilution, at least in animals, was proving to be a pretty effective way to change them. The critics, of course, not everyone was ready to jump on board. Critics pointed out that just because a senescence marker disappears doesn't mean the cell is truly young again. Some worried that reactivating certain damaged cells could lead to uncontrolled growth, even cancer. These are valid concerns, and the Conboys acknowledge them. That's why they stress that more research is needed before anyone can claim this as a cure-all. But even with those caveats, the findings opened a door that many thought was closed. It suggested that aging cells might be more flexible, more capable of recovery than we've been taught. The human connection. If you're wondering how this connects to human aging, here's the exciting part. Senescent cells and age-related inflammatory proteins aren't just a mouse problem. They're found in human tissues too, and their levels go up with age. Theoretically, if you could safely bring those levels down without harming the rest of the system, you might see similar benefits. Better tissue repair, lower inflammation, improved cognitive function. And that's exactly what the Conboys decided to test next. Not just in theory, not just in mice, but in actual human beings. The leap to human trials, the move from mouse to human, is where a lot of anti-aging ideas crash and burn. What works in a lab rodent doesn't always translate to our much more complex biology. But the Conboys had a small advantage. The basic process they were using, therapeutic plasma exchange, was already an FDA-approved medical procedure for certain conditions. That meant it could be tested in humans far more quickly than a brand new, unapproved treatment. So they teamed up with Dr. Dobry Kiprov, a clinical expert in therapeutic plasma exchange, and began pilot studies. The question was simple. If they applied the same principles in people, would they see measurable improvements in health and cognition? The early results would surprise even them and hint that plasma dilution could have benefits far beyond aging research. Human trials and potential. For years, the Conboys' work lived mostly in the world of animal studies, controlled experiments on mice that gave tantalizing hints about what might be possible. But there's always that big leap. Will it work in humans? The good news was that they didn't have to invent a brand new medical procedure to find out. The core of their approach, removing plasma and replacing it with a balanced solution, was already an established treatment called therapeutic plasma exchange, TPE. TPE has been FDA approved for decades for certain autoimmune diseases. In those cases, it's used to remove harmful antibodies from the blood. The Conboys saw an opportunity. What if the same process could be adapted to lower age-related proteins and, in doing so, flip the repair switch back on in older adults? A simple setup with big questions. Working with Dr. Dobry Kiprov, a leader in clinical plasmapheresis, they designed a pilot study. The setup was straightforward. Take a group of older participants. Perform one session of therapeutic plasma exchange, replacing a portion of their plasma with saline and albumin. monitor not just their immediate health, but specific markers linked to aging, inflammation, tissue repair signals, and cognitive performance. The beauty of this design was that it wasn't theoretical. The process was already considered safe when done in a controlled medical setting. The question wasn't if it could be done, but what would happen afterward. What they found? The first thing they noticed was a drop in inflammatory markers. This lined up perfectly with what they'd seen in mice, the first wave of rejuvenation. Within days, the blood's chemical weather shifted toward a calmer, less hostile environment for cells. But the real excitement came from the functional changes. In cognitive tests, some participants showed measurable improvements in short-term memory and problem-solving, the kinds of abilities that often decline subtly but steadily with age. One of the most striking findings was a boost in curiosity and engagement, in a way that mirrored the mice exploring new objects. Some older participants became noticeably more mentally alert and interactive. Of course, these were small pilot trials, not large-scale clinical studies. No one was claiming a miracle cure. But the fact that such changes were seen after just a single session was enough to warrant deeper investigation. How long did it last? That was the million-dollar question. Was this a quick, temporary tune-up, or could it have lasting effects? So far, early follow-up suggested that some benefits, particularly in reduced inflammation and cognitive sharpness, could last for weeks, sometimes over a month. But the effects weren't permanent, and the Conboys never expected them to be. In their view, plasma dilution is more like regular maintenance than a one-time repair. Just as you wouldn't expect one oil change to keep a car running perfectly for life, you wouldn't expect one treatment to hold back aging forever. The real challenge and opportunity lies in figuring out the optimal treatment schedule. Precision medicine approach. One of the most forward-thinking aspects of the Conboy's plan is that they don't see this as a one-size-fits-all therapy. Some people might only need it occasionally, as a preventative measure to keep repair signals active. Others, especially those already facing cognitive decline or degenerative conditions, might benefit from more frequent sessions. This is the essence of precision medicine, tailoring the intervention to the individual's biology, rather than prescribing the same regimen for everyone. Beyond aging, here's where things get even more interesting. The Conboys believe plasma dilution might have benefits beyond just slowing or reversing aspects of aging. Because the process removes a broad range of circulating proteins, it could potentially help in diseases where harmful proteins play a role, from autoimmune disorders to chronic inflammation. It's a bold vision, but one grounded in the fact that TPE already has a track record of helping patients with certain immune-related conditions. The new frontier is applying it strategically to target the molecular changes that come with aging itself. Skepticism and support, and not everyone is convinced. Some scientists worry that removing too much plasma too often could have unforeseen side effects, especially if beneficial proteins are also reduced. Others point out that without long-term, double-blind, placebo-controlled studies, it's too soon to draw firm conclusions. The Conboys agree, which is why they're pushing for larger Phase 3 clinical trials. These would not only test effectiveness, but also refine the protocol, how much plasma should be removed, how often, which biomarkers should guide the decision. If those trials succeed, it could open the door to a scalable, relatively low-risk intervention for extending health span, the number of years we stay healthy and active, rather than just lifespan. The potential impact. Imagine a future where, instead of waiting for age-related diseases to appear and then treating them one by one, We simply maintain our body's repair systems throughout life. In this scenario, aging isn't something we try to cure at the end. It's something we manage continually, like dental hygiene or physical fitness, so we keep our biological systems operating at their youthful best. That's the vision the Conboy's work points toward. And while we're not there yet, the path is starting to take shape. The next and final step in this story, exploring what happens when you combine this approach with other cutting-edge rejuvenation strategies and asking the bigger question, if aging can be reversed, even partially, do we need to rethink what it means to grow old at all? The future of aging research. For centuries, aging has been treated like a law of nature, as fixed and inevitable as gravity. But if the Conboy's work tells us anything, it's that aging may not be a solid wall after all. It might be more like a fog, thick and heavy, but one that can be lifted, at least in part, if you know where to start clearing. And that changes the entire conversation. From cure to maintenance, most of modern medicine is reactive. We wait for something to break, a joint, an artery, a memory pathway, and then we scramble to patch it up. We call this treating aging, but really, we're treating the consequences of aging. The Conboy's approach is different. It's not about waiting for the damage to pile up. It's about keeping the repair systems humming so that damage never gets the upper hand. It's moving from a cure mindset to a maintenance mindset, just as we learn to prevent cavities with daily brushing instead of pulling rotten teeth. Imagine walking into a clinic every year or two, not for bad news, but for a scheduled tune-up of your body's repair signals. No magic pill, no exotic stem cell transplant, just a routine cleaning of your bloodstream's chemical environment so your body can keep doing what it was built to do. Rethinking longevity. If we start thinking about aging as a manageable, reversible process, even if only partially reversible, it shifts how we plan our lives. Right now, old age is a single block at the end of life, a chapter defined by fragility. But what if that chapter could be stretched, reshaped, or even rewritten? A 70-year-old could take up a new career without worrying about losing mental sharpness. An 80-year-old could recover from an injury like someone in their 50s. Retirement could become less about slowing down and more about exploring the decades still ahead. This isn't just science fiction. It's a logical extension of what we're already seeing in the lab and early human trials. The ethical crossroads. Of course, extending healthy lifespan raises thorny questions. Who gets access to these treatments? Will they be affordable or only for the wealthy? If people live decades longer in good health, how does that affect jobs, families, and resources? These are real debates we'll need to have, and sooner than we think. The science is moving faster than public policy. In fact, the Conboy's work is one of the few examples where the barrier to widespread use isn't purely scientific. The technology exists today. What we're missing are the large-scale trials and the framework to integrate this into mainstream healthcare responsibly. Beyond plasma dilution, the Conboys are the first to admit that plasma dilution isn't the ultimate fountain of youth. It's a tool, a powerful one, but likely just part of a bigger toolbox. Other researchers are exploring senolytics to clear out truly damaged cells, partial cellular reprogramming to reset aging at the genetic level, and metabolic interventions like fasting mimetics to improve resilience. The real future of aging research may lie in combining these strategies, each targeting different aspects of the aging process. Plasma dilution could clear the inhibitory signals. Senolytics could remove cells beyond repair. Reprogramming could restore youthful gene expression. Together, they could push the boundaries of what's possible for human health span. The emotional side of the equation. As we age, Connor, it's easy to get lost in the science and forget what this is really about: people's lives. Think of the millions living with Alzheimer's, Parkinson's, or chronic pain. Think of families watching loved ones fade physically and mentally, knowing there's no going back. Even a modest extension of healthy years could mean more time with grandparents, more years of independence, more moments that matter. In one of their interviews, Irina Conboy said something that stuck with me. We're not trying to make people live forever. We're trying to make the years they already have as good as possible. That's a mission almost everyone can get behind. Where we stand. Right now, the Conboy's work is at a pivotal point. The proof of concept is there, in mice, in early human trials. The next step is large-scale clinical validation. That means money, time, and a lot of data. If the results hold up, we could be looking at one of the most significant shifts in healthcare in a century, a move from treating aging symptoms to managing aging itself as a condition. The takeaway, we began this story with a question. What if aging wasn't permanent? Now, we know it might not be. The repair systems are still inside us, waiting for the right environment to wake up and get to work. Sometimes, the key isn't adding something new. It's removing what's been holding us back. The Conboy's plasma dilution research is far from the final word on rejuvenation, but it's a powerful reminder that the rules we think are fixed may only be guidelines, and that biology has more flexibility and more hope than we often give it credit for. A thought to leave you with: if we can slow, stop, or even reverse parts of aging, then the story of human life is about to change, not just for scientists, but for every one of us. The question isn't whether you'd want to live longer. The question is, what would you do with the extra years if they were full of energy, clarity, and possibility? Because that's not just a dream anymore. That's a decision we might all get to make in our lifetime.